Hey kiddos, welcome to Spiral Review 13. First off, we're going to have some substitution and differential equations. And the very first thing we have is a physics-based problem. We're given the velocity, and we've got to find the position. I give you a hint at the bottom that says velocity is the derivative position. So what this is saying is that v of t is equal to, and for position we usually use x prime of t. So the position of x at time t. And if we're trying to find position when t equals pi over 2, we've got x equals 4 when t equals 0. That means we have the point 0, 4 on our graph. And we're trying to get pi over 2, some x value here. And what we're really talking about is going from the derivative to the original function. So this is going to be a antiderivative type problem, and we're talking about some kind of a starting value. So the starting value is going to be 4, and from time 0 to pi over 2, and then sine of 2t dt. So starting plus change is equal to final value. Here I've got an integral that has a function on the inside, so I'm going to make u equal to 2t. du dt is going to be 2, and dt is going to be 1/2. Sorry, it's going to be 1/2 du. Whew. Having fun here with stuff. So that kind of resets this problem as 4 plus, I'm also going to plug in for sine of 2 times pi over 2 would be sine of pi, which is 0. And sine of 2 times 0, sorry, I'm totally messing this up for us by plugging into the function, not into u. So scratch that. If I do u is 2 times pi over 2, that means that in terms of u, we're looking at this as pi, and we're still at 0 on the bottom. Okay, that's a little bit better. So then we've got sine of u, and then we got times 1/2 du. When I integrate this, the derivative of cosine is going to be negative sine, so the antiderivative of sine is negative cosine. And when we do that, we've got 4 plus, I'm going to do the 1/2 out front, negative 1/2, cosine evaluated at pi and at 0. All right, so 4 plus negative 1/2. Cosine of pi is going to be negative 1. Cosine of 0 is going to be 1. So minus 2 times negative 1/2 is plus 1. And that's going to be 5 is our answer. For the next one, we've got dy dt is equal to this thing, and we're given some kind of an initial value. We've got to find y of 6. Let's separate our variables. I can't talk today, apparently. And if we do that, we get dy is equal to negative 10 e to the negative t over 2 dt. I also might move the y to the negative 10 to the y side just to make this fancy part by itself. So I get negative 1 over 10 dy is equal to e to the negative t over 2 dt. Okay, now I'm going to integrate. And I've got negative 1/10 dy, so that's going to become negative 1 over 10 y. And then on the other side, we've got e to the negative t over 2. I've got a u of negative t over 2, which means that du dt is going to be negative 1/2. dt is going to be negative 2 du. So on this side, that would become e to the u times negative 2 du. E to the u is going to be e to the u. So we've got the negative 2 out front, so negative e to the negative t over 2. I'm going to plug my u back in, and then I'm going to have a plus c. I forgot my negative 2. Okay, we're going to use our initial condition. So if I plug in 0 for t, I should get 20 for y, so negative 1 over 10 times 20. And if I plug in 0, that means I've got negative 2 plus c. Negative 1/10 of 20 is going to be negative 2, which means that c is equal to 0. All right. Let's then kind of give myself a little bit more room. And in this process, we've got negative 1/10 y is equal to negative 2e to the negative t over 2. And we're looking for y of 6. I'm going to multiply both sides by negative 10 to give us y is equal to 20. And then plug in 6. E to the negative 6 over 2 is negative 3. So 20e to the negative 3. That appears to be answer choice B. Ooh, and I got a nice big thing that doesn't zoom out. Next up, we got to find some areas. We're looking for the area bounded by the curve x to the 2/5 plus 1/4 x and negative square root of x plus x. The first thing I might do is to find the intersections, and I'm going to use my graphing calculator to do that. And when I do that, I get a graph that looks something like this, where the x to the 2/5 plus 1/4 x does one of these bad Larrys, and the negative root x plus x is going to do something that looks like this. The first place that they have an intersection would be 0. And then our goal is to find this other part. And to do that, I'm going to do second calc intersect and get somewhere close over to there. Which is going to take a second for me to slide over. And then when I press enter, we have an intersection at 5.993, which I wonder if that's supposed to be 6. And when I take a look at that, in fact, it is just 5.993. So if we're trying to find the area between these two curves, we're going from 0 to 5.993. It's going to be x to the 2/5 plus 1/4 x. And then that's minus the square root of x plus x dx. To be honest, this is what I'm looking for on your spiral. The answer for this is going to be much less important than the setup for the problem. So when I use fn int for this, we're going from 0 to 5.993, x to the 2/5 plus 1/4 x minus the square root of x and x. I just want to make sure that I put a times in there. I've got to put an x at the end to indicate the variable that I'm choosing to use. And after some thinking, because it takes a while for the calculator to do this for us, we get a value of, well, okay, there we go. Negative 14.4879, which means that I may have selected the wrong order of things. Okay, I did some research, and I figured out that I lost a negative in writing this in front of that. Oh, good, I'm going to change the color so you can actually see what I wrote. In front of that square root. So the answer is going to be 5.0737. All right, next up we've got the base of a solid with 100 minus x squared, which by the way is a semicircle. And each cross-section is going to be a little bit different here. So I'm just going to kind of sketch this so I have an idea of what's going on. And here we're going from -10 to 10. You're welcome to graph this to get those values if you need to. And we're going perpendicular to the x-axis. So an isosceles right triangle, that's a beep. With a leg in the plane is going to look like this, where we have a side, it's isosceles, so coming out of the plane would be a side also. And the area of this would be 1/2 side squared. And if the side is going to be this equation, we're talking about the integral from -10 to 10 of 1/2, that's going to be the square root of 100, minus x squared dx, which if you want to simplify that before evaluating, so -10 to 10, and that's going to end up being 50 minus 1/2 x squared dx, which is going to be 50x minus 1/6 x to the third, evaluated at 10 and -10. So it's going to be 500 minus 1/6 of 1,000. That sounds fun. So 1,000 over 6. And then whatever that is, which is going to be 3,000 minus 1,000, it's going to be 2,000 over 6. That's for the top part. And then do the same thing for the bottom part, and you might notice that both of these are going to be negative. So I'd end up with minus -2,000. Zoom a little bit. Over 6 is going to be 4,000 over 6 is your final answer. Totally okay if at this point you plugged into your calculator and used fnint. All right, same equation, rectangle's base in the xy plane, height 3 times the base. So you've got a base and then 3 base. So if your base R belonged to us, we've got areas being added up here. Going from -10 to 10. I'm going to say that the area is 3b squared, where b is again that equation. So we've got 3 times the square root of 100 minus x squared dx, and again that's the most important part of this problem. We're going to end up with that squared, so 300 x, and then that's going to be minus 3x squared, but it's going to be 3x to the third over 3, which is going to be x to the third, and at 10 to -10. Okay, this is going to be, again, we're doubling the piece of this once we get the first half, so it's going to be 3,000 minus 1,000, which is 2,000. And from that, I'm going to subtract the same thing, but negative, which is going to give me a value of 4,000. And then finally, we've got the free response thing. We've got, this one is given to us algebraically. We're given a function. We're also given the derivatives, so we don't have to worry about that, although that's the quotient rule in case you were curious. We've got to write an equation of a tangent line to the graph at x equals e squared. Okay, we know the tangent line is going to be in a point slope form, so it's going to be y is equal to y1 plus some kind of slope times x minus x1. For the y1, I'm going to plug e squared into my original equation. So f of e squared is going to be ln of e squared over e squared. Ln of e squared is going to be 2, and that's going to be 2 over e squared. Okay, so that's my y1. So let's start to build this. So y is equal to 2 over e squared. And then for my m, I need a slope. So I'm going to have a derivative there, but hold on a second. I just want to fill the rest of this in. And then that's going to be minus e squared, because that's the point of x that I'm using. Okay, so let's find the derivative. And, oh wait, we already have that, so we're really just plugging this in. F prime of e squared is going to be 1 minus ln of e squared over e squared squared, which is e to the 4th. E squared we said was 2. It's going to be negative 1 over e to the 4th. So negative 1 over e to the 4th. At this point, you're done with part A. Part B. Find the x-coordinate of the critical point of f. In other words, we're going to have when x is going to be equal to 0, oh sorry, when f prime of x is going to be equal to 0. We also have an issue with x equaling 0 here, but that's also non-existent in our original function, so we're not going to worry about that one. So what we're talking about is when f prime of x is equal to 0, which is equal to 1 minus ln of x. I can say this because I know that the denominator does not come into play when finding 0, because 0 divided by any number other than 0 will give us 0 as an answer. So that tells us that 1 is equal to ln of x, which means that x has to be e. So that's the x-coordinate. Whether this is a min, a max, or neither, I could either do this as a second derivative rule, or maybe just take a look at what's going on here. I'm going to set up my sentence frame before I do any math, so I'm going to say at x equals e, f prime goes from blank to blank, so f of e is a, and I'm putting another blank for max or min there. Okay, so just to kind of check, we've got e, we're going to maybe put a number like 1 in, because 1 works nicely for e things, and maybe put a number like 10 in, or maybe even e squared, because I got some points for that earlier. In fact, I already have that value, which is nice. So f of e squared was negative 1 over e to the 4th, which is a negative value. And f of 1, well, 1 minus ln of 1 is 0 over 1 would be a positive value. We're going from positive to negative. So therefore, we're going from an increasing to a decreasing. Therefore, it is a max value. For part C, we've got the graph of the function of f has exactly 1 point of inflection. This is something I was hoping I would not have to do, which means that we have to find f double prime. And when we work with this, so we're going to have to do a quotient rule here. We end up with the bottom, x squared times the derivative of the top, 0, and then minus 1 over x, minus the top, 1 minus ln of x times the derivative of the bottom, 2x, all over the bottom squared. That would be x to the 4th. I might notice that I can take an x out of both of those and make this x to the 3rd. I might further notice that I've got an x and a x on the bottom there, making that a negative 1. So we get negative 1 minus 1 plus ln of x over x to the 3rd. So minus 2 plus ln of x It's actually kind of an interesting derivative. F double prime is equal to minus 2 plus ln of x over x to the third. We got to figure out where this inflection point is. That's going to be when this is equal to 0. We've already established that 0 in the bottom is not going to be helpful for us here. So we get ln of x is equal to 2, which means that e squared is equal to x. So that's a critical value. We have to judge if this is changing here. And when we do that, so we're going to look at e squared, maybe e to the third, because these seem to be pretty good to plug in, and maybe 1, because that seems kind of nice too. And if I plug in 1, we're going to have minus 2 plus 0 over 1 is minus 2. If I plug in e to the third, that would give me 3 here. So we have negative 2 plus 3 is 1 over a positive value. It is a point of concavity it's a point of inflection because we are changing sign for the second derivative. I'm not actually asked to justify that, so you don't need to go that far. And then the last part of this is we got to find the limit as x approaches 0 from the right of the function. All right, I'm going to do part D kind of up to the side. So we've got f of x is equal to ln of x over x. And we want to find the limit as x approaches 0 from the right. And what I'm going to do is to kind of try to make some sense of what's going on here. Ln of 0 is going to be undefined, but from the right, we know the graph of ln does something like this, and I've got an asymptote at 0, so that'd be like negative infinity-ish. And it's negative infinity over 0. I'm going to do some bad thinking here and say that this is going to be negative infinity divided by 1 over infinity, which is the same as negative infinity times infinity, which is going to be negative infinity as a value. So the limit as x approaches 0 from the right of ln of x over x is going to be negative infinity.